Scheduling and Production Activity Control (PAC) methods provide the framework for translating production plans into executable activities while maintaining alignment with customer demand, resource availability, and operational objectives. A primary distinction in scheduling environments is between batch and flow manufacturing. Batch manufacturing produces products in discrete lots that move through work centers according to routing requirements, making scheduling more complex because of setup times, queue accumulation, and varying product priorities. Flow manufacturing, in contrast, emphasizes continuous movement of products through dedicated processes with minimal interruptions. Because flow environments typically support standardized products and repetitive operations, they require simpler scheduling methods and benefit from shorter lead times, lower work-in-process inventory, and smoother production flow. Creating effective work sequences is essential for maximizing efficiency and balancing supply with demand. Schedulers use priority rules, resource calendars, and time fence policies to establish production order, while ensuring that critical customer commitments are met. Time fences protect portions of the schedule from frequent changes and provide stability for operations and material planning. Resource calendars identify machine, labor, and maintenance availability, helping planners avoid unrealistic schedules. Load calculations combine released orders, planned orders, rework requirements, and work in process to determine resource requirements at each work center. Accurate sequencing minimizes setup changes, reduces waiting time, improves capacity utilization, and helps organizations respond effectively to fluctuating demand while maintaining schedule reliability and production performance. Push and pull scheduling systems represent two fundamentally different approaches to controlling manufacturing operations. Push systems rely on forecasts, master schedules, and MRP-generated plans to release work into production based on anticipated demand. Flow of materials is driven by planned schedules, making coordination highly dependent on accurate forecasts and planning data. Pull systems, however, authorize production only when actual demand signals trigger replenishment activities. Lean manufacturing environments commonly use pull systems to reduce inventory and synchronize production with customer requirements. While push systems are generally better suited for high variety and customized environments, pull systems perform best in stable, repetitive operations. Understanding the strengths and limitations of each approach enables organizations to select appropriate scheduling methods. MRP-based scheduling, lean scheduling, and theory of constraints, TOC, scheduling each offer unique methods for controlling production. MRP-based scheduling focuses on minimizing backlog and lead times through detailed planning of materials and capacity. Lean scheduling emphasizes rapid flow, low inventory, and demand-driven replenishment, often reducing the need for detailed work order scheduling. TOC scheduling concentrates on maximizing throughput by identifying and managing system constraints. While MRP systems rely heavily on planning accuracy and transaction processing, lean systems depend on standardized work and visual controls, and TOC systems focus on bottleneck performance. Selecting the appropriate scheduling methodology depends on manufacturing characteristics, product variety, demand patterns, and resource constraints within the organization. Managing bottlenecks is a critical responsibility in both lean and TOC environments. In lean systems, bottlenecks are addressed through waste elimination, process balancing, standardized work, and continuous improvement initiatives. TOC views the bottleneck as the system's primary constraint and focuses improvement efforts on maximizing its utilization. TOC scheduling follows a structured process of identifying the constraint, exploiting it to maximize throughput, subordinating other resources to support it, elevating the constraint's capacity, and repeating the cycle when a new constraint emerges. Effective bottleneck management improves throughput, shortens lead times, reduces queue accumulation, and enhances overall system performance. Organizations that proactively manage constraints gain greater operational flexibility and more predictable production outcomes. Lean scheduling seeks to synchronize production with actual customer demand through concepts such as takt time, production leveling, and Kanban control systems. Takt time establishes the required pace of production by dividing available production time by customer demand, creating a rhythm for operations. Production leveling, or hijunka, smooths volume and product mix variations to stabilize workflows and reduce operational disruptions. Kanban systems support pull production through visual signals that authorize replenishment. One-card Kanban systems typically control production or movement activities, while two-card systems separate production authorization from material movement authorization. These tools minimize inventory, improve responsiveness, reduce waste, and create greater visibility across manufacturing operations. Input-output control plays a significant role in maintaining desired work-in-process levels and controlling queue times. By comparing the rate of work entering a work center with the rate of completed output, managers can identify imbalances before congestion develops. Excessive input relative to output increases queue times, extends lead times, and creates inefficiencies throughout the production process. PAC procedures support this control through work authorization, order release, progress monitoring, and feedback reporting. Typical work order release steps include verifying material availability, confirming capacity, authorizing production, issuing work instructions, and tracking execution. These controls help maintain schedule integrity while ensuring resources are utilized effectively and customer commitments are consistently achieved. Process industries introduce additional scheduling complexities because production often occurs in batch, discrete, or continuous modes using interconnected process trains. Process flow scheduling focuses on balancing material movement, equipment availability, and resource constraints to maintain uninterrupted operations. Organizations must manage both standard and non-standard demand while accounting for unplanned loads, maintenance requirements, and industry-specific conditions that affect capacity. A key distinction exists between process-dominated and material-dominated scheduling. Process-dominated scheduling prioritizes equipment utilization, sequence optimization, and flow continuity, whereas material-dominated scheduling focuses on material availability and inventory constraints. Effective management of these factors enables organizations to balance flow, optimize throughput, reduce interruptions, and maintain efficient operations across complex manufacturing environments.